want to just make sure that we have a small understanding, of the difference between these two things. First, if you're trying to get an impression for how do you deal with the two ideas, they're both developed from completely separate places. They work cooperatively to help us understand the nature of how charges interact. So, in the shortest possible manner of doing this, I want to remind you of just a couple little things. If I put a single charge in space, then you probably already know that another charge will feel a repulsive force due to the first charge. Any question about that? Right, so if I take that charge and move it over here, you're aware, because of Coulomb's law, that it would still experience a repulsive force, but that force would be larger now because I am closer to the particle. And directed in a different direction, because although closer, I've also shifted where I am relative to the particle. This would occur no matter where I place this second charge. It will experience a force. That force will be related to how close I am to the first charge and will be directed away from the charge. The electric field is an attempt to get an expression for the space around any configuration of charges. Something that lets us know what the electric field could be at any location, which in turn tells us what kind of force a charge would feel at any location. The electric field is analogous to force. They are developed together because they are directly proportional to each other. If you know the electric field, you know the force on a charge placed where that electric field is known. That's all the electric field is. It has a direct analogy to force and is based on force. So anything that we know about force can state the same things about the electric field. It's a vector. It has a direction. The difference, of course, is that in many of the things we talked about last year in mechanics, when dealing with forces on objects, the only field we ever dealt with was the gravitational field, and for 6 to 8 months, that was a constant. So all of our interaction with dealing with that force dealt with something that was the same all the time. If I wanted to deal with the gravitational field, all I ever did was say weight is equal to mg. This is no different than saying force is equal to QE. No different, except that G was a constant near the surface of the Earth. Well, E, we have plenty of expressions for electric fields that aren't constant. But this is the same relationship. Eventually, we would come up with a different relationship for G, one that looked like this. Newton's law of universal gravitation. No matter whether you're in AP1 or in mechanics, we talked about this. It's not weird that the electric field around a point charge looks exactly the same. They're both inverse square laws, which is what makes them conservative laws. The difference is, with gravity, most every mass out there that we worry about that has gravity associated with it is spherical and is treated as a point mass. Right? Planets, sun, stars. Suns and stars are the same. Planets, moons, stars. There we go. But we can configure charges in lots of more interesting shapes and arrangements. So we have many expressions for the electric field that aren't just like a point charge and aren't constant. But the only difference still between what we studied last year and what we're studying now is that we often look more at the electric field than we do an individual force. That's the only difference. Now, in addition to that, when we develop the idea of force, we then develop from the idea of force work, and from work energy. We talked about the energy of objects because in mechanics, we generally had an object to which we were focused. A roller coaster car, a pendulum bob, any one of a number of things, we focused on an individual object. It shouldn't be lost on you that we could have a new concept or a new idea that is related to energy. Oh, I got that backwards. In the same way that force is related to the electric field, we have a relationship that's similar. It's energy. It's the voltage. When we talk about finding the electric potential, we are really talking about energy in the same manner in which we would have talked about energy in mechanics. Again, in mechanics, to be simple, we had more simplistic starting points. Gravitational field. We talked about this object experiencing a force downwards weight equal to mg. But that if we moved it to A or moved it to B, we were changing something about the object. And we talked about if we move it to A, it would take work to do so, but we could store that work as potential energy in the object. We could get that energy back by just releasing it. And similarly, we know just from studying this that it would take more work to get from our starting point to B than it would to get from our starting point to A. And you would be able to look at this directly and know that there would be more potential energy here than there would be here. None of this should be a surprise to you. This is all the stuff we did already. And even when I developed or talked about the concept of electric potential, I indicated the point of electric potential was to mimic the way we deal with energy, but without having to associate it with a specific amount of charge. In the same way that right now, if I asked you where would this mass have more energy, at B or A, you should be able to tell me that answer. You should know that moving it from the ground to B requires more work, so it has more energy at B than it would at A. Now look, I'm saying all this and I'm repeating myself. So I'm gonna hit pause. The electric field is the same idea, except we don't have this uniformity all the time. We have electric fields that are sometimes complicated. And one of this example, if I want to go from here to here, it didn't matter that I went through a complicated path. Roller coasters were complicated paths. But all we cared about was the absolute change from where it started to where it ended. We didn't care where the track went. Examples is still just dealing with a point charge. If I put a point charge here, all of you should be able to wrap your head around the idea that there's an electric field that looks something like this around this charge. And no surprises, the electric field is more concentrated as I get closer. It's harder to move closer the closer you get. That's just because the electric field gets stronger the closer I get. So when I think about moving a particle from very far away to here, or then moving that particle to here, or then moving that particle to here, 3 different locations, but I know it would be hardest to move it to A and easiest to move it to C if I'm starting from very far away. In fact, we did the math on it. We found out if I want to move my charge Q closer to my big charge, capital Q, then the amount of energy it would take, the electric potential energy, would be QQK over R. We did this. In fact, I'll remind you, we calculated the electric potential. The electric potential would be QK over R, assuming we started from infinity far away and moved to a distance R away from the charge. And at the same time, just even a moment ago, I wrote this on the screen. So this is no surprise. This is how much energy it takes to move my little charge, little q, anywhere. Once I get there, I could talk about the change in potential energy for little q, and going from like C to maybe B, or maybe from B to A, or C directly to A. In those cases, I have how much energy it takes to get to each of these points. If I wanted to find the change, well, I'd probably have to take the amount of energy it would take to get to B and subtract how much energy it would have taken to get to C. If I want to make them relative to 0, this would be the change in energy in going from C to B. Any question about that? Now, this may not have been made clear, but this is path independent. It doesn't matter what path I take to get there. It's no different. That's got to be true here as well. Now, I don't want to spend a lot of time on this particular picture, but I do want to impress upon you the idea that we want to develop this same concept, but without having to think about a particular charge. That's why they ask about the electric potential. It doesn't change very much here. When I want to deal with just the electric potential, then I stop thinking about the individual charge and I start thinking about the space, the location, where I am. So suddenly when I bring those places back to my mind, C, B, and A, then I want to ensure that you understand that these locations tell us something about the energy. So the electric potential at C is just QK over C, because it's about this charge and what it's doing to the space. But it's also about the amount of work it would have taken to get a charge to this location, or this location, or this location. Dealing with the electric potential isn't any different than dealing with the energy. The reason we deal with the electric potential is we sometimes don't know how much charge we're going to be dealing with. The whole formulation of electronics gets rid of the individual object and puts it in terms of any object. So electric field isn't about force, it's about force per unit charge. And electric potential is about energy. It's about energy per unit charge. That's why this is a joule per coulomb and this is a Newton per coulomb. Now, you guys are smart people, so pay attention to this. A joule per coulomb is a Newton meter per coulomb. Good? Now, Newton per Coulomb electric field. Do you see it in there? Now, a volt is a joule per Coulomb. What did I just say? I got distracted when somebody knocked on my door. If I solve this for joules, I get volt Coulomb equals a joule. Okay? And volt Coulomb equals Newton meter. Just doing the little math here, okay? Now, I want to write this as volt Newton Coulomb meter. I did this because I wanted to be able to break out the joules separate, but now I'm putting the newtons back over there. And I'm going to divide by meter, and I get volt meter equals Newton per Coulomb. But this is electric field. The unit of electric field can be written in terms of volts and not newtons. Now, Mr. Sheldon, why would you bother to do that? Because if you'll notice, going from here to here cost you meters. You're moving against the field. This expression tells you how many volts it will cost you per meter to move. It's directly related to whatever the electric field is. Moving around in an electric field costs you energy. It costs you a certain number of volts for every meter that you change. That's what the electric field is really about. What I want you to understand is you can do all the math we did so far, the first 6 weeks of school, by only talking about voltage. Or you can do all the math we did at the beginning of school by only talking about electric field. Electric field and voltage are derived together. So part of what I was trying to, this picture could do that for me. So let me try and see if I could do this here, but I don't know if I can. Because I don't know if I can draw it well enough for you to see what I want. Would everybody be able to agree with me that A, B, and C all lie different distances away from my point charge? Now, gotta find something here. This is A. Would you agree that that distance away, anywhere in this circle, that distance away, would be at the same voltage? Does that make sense? So consider a circle right around there. All of this is at the same voltage, voltage of A. And there's going to be a similar one at B. This is at the voltage of B. And then there's a similar one that's at the voltage of C. These are considered equipotential lines. They are all at the same potential. I tried to compare this yesterday with elevation. This potential is higher than this potential. And that potential, B, is higher than this potential. Everybody okay with this so far? You sure? Because if we look at this, we can get rid of looking at the electric field. Like get rid of all these individual electric field lines and consider that These would represent equipotential lines. Without the field in place, this is higher than this, which is higher than that. To consider what we're trying to say here is that it's like going uphill to go from a place over here to a place over here. A ball would naturally roll downhill. It would naturally roll towards lower levels. So if I put a charge here, it's going to want to go from a place of high potential to a place of low potential. It's being driven by the electric field, but you could think of it as elevation. It loses voltage for every meter that it travels. As it goes this way, it's traveling through equipotential lines. And for each one, it loses some of its potential energy. So it's going from a place of high potential to a place of low potential. It'd be no different than saying, my charge creates a landscape like this, where this point in the middle is where the charge is located. And there are equipotential lines around it. This would be a cross section. We're looking at it from the side where this is VA, this is VB, this is VC. I've tried to draw it in such a way that it represents 1 over R squared, the electric field. 1 over R, the electric potential. So that it has that kind of curve to it. But if you place a positive charge here, does it give you the mental idea that it would roll down this ramp? Part of the reason I want you to see that is because of the way this looks. If you change this to be a derivative, you get that E is going to be equal to minus dV dr. This is a graph. V in that direction. R in this direction. The slope of this graph is the direction of the electric field. But more than that, the electric field points in the opposite direction of that slope. So where this is a positive slope, the electric field must point that way. Well, that makes sense, right? Wouldn't it push the particle this direction? So if you're moving towards a place of increasing voltage, the electric field must be pointing away from you. Just another way to say the same things we've been saying. Now, still trying to give you an idea of the difference between electric potential and electric field. Let me kind of bring you back to some other topic, because somebody's going to ask about this question. Bless you. Ring of charge. Total charge Q on the ring. There should be no doubt that in a general way, the electric field points away from the ring. But I couldn't really tell you what the electric field looks like here. I couldn't tell you how strong it is. It's off axis, and that'd be a complicated calculation for all the contributions of all the DQs around here to tell me what the electric field is there. But I know it's got to point probably this way, right? It's going to push a positive charge away from the ring. But I also know that the electric field is 0 right there in the center. So I know right now, if I ask you what the voltage is at the center, there are a whole bunch of you who will say it's 0, because you're not thinking it through still. The electric field is 0 there because I have a ring of charge. And when I put a charge there, when I think about the forces on a charge at this point, it's being pushed in all those different directions. Each one canceling out another one. But electric potential isn't about force. It's about what it would take to get to that point. From some place where there was no energy. Would it take work to get a particle from a place that's far away to that point? Yeah. Now, once I get there, it might stay there. That's because the field is zero there. But that doesn't mean it doesn't take work to get there. That's not different than this. There are forces on a charge placed at the center there. Lots of them, pushing it equally to the left and right, up and down. But it will still take energy to get there. In fact, you know what the electric field is. You should be able to take that electric field and calculate how much energy it would take to get from infinity to the center. This is a statement of the, I don't know why I put a negative sign there. This is a statement of the electric field. We solved for this, do you remember? Z represents a distance along this blue line. We could solve for it still. We could say V equals negative E dot dz and do this calculation. And some of you can't do this math, but some of you can. So for those of you who can, let's do it. We're going to go from infinity to zero. All of you say you know calculus. This is just calculus. I'm going to put my q, k, z over z squared plus r squared to the 3/2 power dz. This is a U sub problem. So all of you who have had calculus know U sub. You guys are just starting calculus, you don't. So I'm not saying you, but I'm saying everybody who finished calculus last year. No trouble, right? I would sub in for you z squared plus r squared to the 3/2, or I'll just do z squared plus r squared. That means du equals 2z dz. Let's do the substitution. For the time being, I'm going to move that q and k outside because they're just constants. And I'll get z over u to the 3/2 times du over 2z. Everybody good with all those substitutions? We follow that okay? If you've done U sub, you know what I'm doing. If you haven't done U sub, just chill, relax. Because I'm coming for you next. Because you could have done this problem a lot easier and you didn't. Now, this is a pretty straightforward integral though. So for all of you who, haven't done U sub, you should still do this. A polynomial, the z cancels. So I'm going to bring that 2 out front. And I'm going to do the antiderivative of u to the negative 3/2, which is going to give me u to the negative 1/2, right? Times negative 2. Evaluated. Well, I'll do the evaluation later because I converted to u. So, any question about this? Add 1 to the exponent, divide by the new exponent. We're all good? Just making sure. I got some quizzical faces out there. If you've been through calculus, you should be able to do this. If you haven't, just chill. I'm not worried about you. All right. That means this becomes negative q over k times 2. And I'm going to plug in my original function, which is 1 over z squared plus r squared to the 1/2. Times, well, I might as well put that negative 2 on top. Why not? So this is 1/2. And I'll put that negative 2 on top. Why not? There's negative 2. I'm going to evaluate from infinity to 0. 2 and 2 cancels, negative and negative cancels. So this is just qk times 1 over, I'm going to put 0 in for z. So that's going to be r squared to the 1/2 minus 1 over, I'm going to put infinity in for z, so that'll be 1 over infinity squared plus r squared to the 1/2. Well, that's 0, right? 1 over infinity squared to the 1/2 is 0, but it's still 1 over infinity. And r squared to the 1/2 power is just r, so this is qk over r. That's got to be the electric potential at the center. That's the math. Now, you might not be able to do that math. Do we not have an expression for the electric field of a point charge? And isn't it qk over r? Isn't that the electric potential for a point charge? So if we had a point charge and we moved a charge close to it, we would have done all that work and we would have gotten the derivation, and that would have been our electric potential for a point charge. All good? Can't we break the ring up into little pieces of charge? Didn't we get trained on how to do that? Can't I say that this is a piece of charge, dq? I'm bringing this up because we did this problem already. It looks like this. There's no reason why we can't do it like that here, right? There's just lots of charges to add up. So I'll have to express dq perhaps in terms of, say, lambda dot r d theta. I'm skipping steps, but can I skip all those steps since we've done all those steps many times before? And I'd say lambda would be equal to q over 2 pi r. Are we all good? So wouldn't the individual electric potential be equal to dqk over r? But isn't every single dq the same distance away from the center? So if I substitute all of that, I'll get lambda r d theta times k all over r. I think I can go ahead and add up all of the contributions, right? From 0 to 2 pi. Yeah? Am I okay? Won't this be the total electric potential at the center? Just adding it up like we would do with 4 charges. Put out my lambda and my r and my k and my other r. And yes, these do cancel. And I have the integral from 0 to 2 pi of d theta, which is just 2 pi, right? I don't have to go into all the details there, like put in a theta to the 0 power, increase its exponent by 1, divide by the new exponent. I don't have to do all that anymore, right? We all know that's just going to be theta evaluated from 2 pi to 0. I'm sorry, from 0 to 2 pi. So this will be lambda k times 2 pi. This has got to be the electric potential. However, lambda is q over 2 pi r times k times 2 pi. So electric potential, qk over r. It has to work this way. More importantly, those of you who were worried about the fact that I asked what would be the electric potential if I came in from a different direction, does it change which direction we go to? It's path independent. This would still be the way to calculate it. Mostly because I don't have an expression for the electric field along this line. So I can't evaluate it that way. But that's not the point. The point is, once I figured out an expression for the electric potential for a point charge, I can apply it the same way that I applied the electric field for a point charge. So, in any problem that we have where I have to calculate the electric potential, you could break it up into lots of little charges. Or you could integrate if you have an expression for the electric field. Either one will work. Would the particle, once at the center of the ring, be stuck there? Well, forever? I can't talk forever. I know that if it was at the center and nothing disturbs it, it will stay there. But if it's displaced in any direction, even a small amount, it will experience an unbalanced force. Now, what happens will probably depend on in what direction it's pushed. If it's just pushed a little bit towards the top, then I don't know that it will leave this area. If I move it this way, it might just be pushed back and do something like that. But if it's pushed this way, we know the expression for the electric field immediately says there is an electric field on the particle that pushes it away, and it will now take off in a straight line. All right. I believe in your ability to read quite a bit. Or do you want me to look at it? Fine.
Separated by a very large distance, have to be traveling toward one another in order to overcome the repulsive barrier in order to reach each other. This barrier is not a physical barrier, but is a separation distance required so a strong nuclear force to take over and bind the atoms together, which is approximately 2 femtometers. Assume you have to get the particles that close.
How far?
2 femtometers.
Okay.
Assume you have to get the particles that close together just so you can see. Now, for fun, consider the kinetic energy of an ideal.
All right, let's just do this one first, right? We can do it from the reverse, right? I could figure out how much electric potential energy there is in constructing 2 deuterium atoms 2 femtometers apart, release them, and see how fast they're going when they're very far apart. And that would have to be how fast they had been shot towards each other in order to get to this point and just stop, correct? So there's this state of the problem, and then there's the state of the problem when they are very far away and traveling with great velocity. All right? Well, the electric potential energy to put the first particle there is nothing, right? Putting one charge in place costs you nothing. It's the second charge that matters. So putting the second charge there, the amount of potential energy required is going to be equal to Q times the electric potential from the point charge of the first deuterium atom, which is going to be Q times QK over the separation distance, which in this case is 2 femtometers. Now, a deuterium atom is a proton and a neutron. So this ends up being the charge of a proton, which is E squared K over R. That's the amount of potential energy that would exist in the combination of both deuterium atoms when they are 2 femtometers apart. So I'd have to put 2 in for this. That'll get you a number. Now, to find out how fast they're going, I would probably say that they're going to convert all that energy into kinetic energy, each one of them taking half of that energy away. So I'm pretty sure I could use this relationship to figure out how fast they would have to be moving from very far away in order to come together and just stop 2 femtometers apart. You'll need the mass of a deuterium atom. But a massive deuterium atom is a mass of a proton and a neutron. You can look that up. Is that sufficient? Is there more to the problem that you need me to talk about? All right. Interestingly enough, if you know a little more about thermochemistry, temperature and kinetic energy are related by the Boltzmann constant. So you can use this amount of kinetic energy to estimate the temperature that this would have to be for these particles to do this. And if this were happening in a star, say a sun, you could do the reverse. You could base the temperature of that star on what kind of processes are going on in its center. Did we not find the electric potential at the center of a square? Isn't that just adding up individual charges to find out the electric potential at the center? So a post, just a post, something like this. And the ground is down here. And I want to take a pebble and put it from the bottom here and set it on top of that post. Will it take work to do so? Because I have to work against gravity to lift it up and put it on top of the post. When I get there, would you agree when it's sitting up there at the top of the post, the net force on it is 0? I didn't say there weren't any forces on it. There are forces acting on it. But the net force is 0. Because of that, it'll just stay right there. Does that mean there's any, that it suddenly has no energy because it's there? Yesterday was a map. So